folks. Today we're going to be doing or discussing sum and difference identities. All right. According to the original calendar, I had it scheduled that we would cover these three things on the same day. The videos are kind of getting long, so 2 or 3 hours. So what I'm going to do to kind of cut down a little bit, since I have the time to take advantage of, I'm going to just do section 9.2 today. All right. Let me just remind you of something. Originally scheduled, we were like this. We would have done 9.2, 9.3, and 9.4. And then we would have had a review day next week. So what I will do, since we're not going to obviously have a review day, and we're not going to have a test day for test number 3, I'll give you the test, but you can just have it. I can't collect it from you for the same reason I've been mentioning. But what I'll do is I'll space this as such. All right, today we'll do section 9.2, sum or difference identities, how to use those. 9.3, which is Tuesday next week, is the double angle, half angle, and reduction formulas. Formula and identity are interchangeable, these phrases, for all intents and purposes. And then on Thursday of next week, we'll have product to sum and sum to product identities. Right. Now, in terms of the handouts, right, what I would have given you today, and it will be available in Canvas, is a handout that looks like this. Right. It's the other half of a handout that I had given you previously. So let me show you 2 of these things. I want to have you sort of collect them all in one place. Right. Here is what would have been the first page of a 2-page handout. All right. There's this one with the triangle man here. We had discussed these identities, all right, for section 9.1. and potentially use some of them for section 9.5. It's kind of goofy. I'm not sure who decided that we would do 9.1 and then 9.5 and then go back to 9.2, but hey. All right. Anyhow, you in theory have this already. All right. But there was a second page to this which I didn't give you at the time, and now I will. All right. The page that I want you to have handy is a list of further identities, which will be for section 9.2, 9.3, and 9.4 respectively. If you are so inclined, maybe divide it up like so. All right. There's a triangle lady here. All right. Anyhow, section 9.2 formulas are from here to here. All right. So if you want to, if you have this printed out, maybe scribble a line to separate. All right. This pertains to 9.2. All right. These, the double angle, half angle, and reduction formulas, they pertain to section 9.3. And then Thursday of next week will be product to sum and sum to product. Right. All right. What I'm going to do now is basically walk you through maybe 1 or 2 problems, and that's it. Right. As for how these are derived, they come from right triangle trigonometry. Technically, transformations, specifically a rotation of an angle, and the distance formula from, which itself is derived from Pythagorean theorem. The distance formula is the difference of 2x's squared plus the difference of 2y squared, all under a square root, right? Anyhow, I'm not going to go into the gory details. Let me just do these, just show you how to utilize these. All right, let's see. And a little bit of a strategy for selecting them. Let's see. If you had a problem that looks like this, finding the exact value of this function, the cosine of 2 angles, 5 pi over 4 minus pi over 6. Couple of things that you would do for a strategy. All right. Number 1, all right, decide whether you have a sine, a cosine, or a tangent that you're working with. All right. Number 2, decide whether it's a sum or given to you as a sum or if it's given to you as a difference. This is beginning to sort of fade out, so let me put this aside. Let me write that a bit more legibly. Okay, and then basically consider your lists basically of identities to choose from. All right. Another side note, and this will be important later, is to remember your special right triangles for references. The 30, 60, 90, and what the sides would correlate to. And then if necessary, when you're drawing something, you could adapt it to a reference angle like these. Square root of 2. Never forget special right triangles. It's technically 90 to be twitty. Okay. All right. So in this particular case, all right, again, since we have established identities, and I'll again flash this here, the blue highlight here. Sum of difference formulas of cosine, sum of difference formulas for sine, and those also for tangent. Given, naturally, the cosine of 2 angles, right? We would be looking basically zeroing in on those that pertain to cosine, all right? And then a difference because of the minus that's here. All right. Now the one that would be appropriate to use is this one. Let's see. The cosine of 2 angles, we're just to distinguish one angle from the other, call them alpha and beta. Let's see. Cosine of alpha minus beta is equal to the cosine of alpha, the cosine of beta, plus the sine of alpha and the sine of beta. Again, just to give you some kind of level of comfort, these are derived from Pythagorean identity, right triangle trigonometry, transformation of an angle that is rotated, and the distance formula of a circle. So this is not malarkey, right? I'm just, for lack of space, not going into that. All right. Anyhow, you're going to basically substitute. So you've opted for the correct identity. All right. Now just decide what sits here and here. Well, this is the first one, so in theory 5 pi over 4 would be the alphas. All right. And pi over 6 would be the betas. All right. The thing is that in order to relate this back to special right triangles, right, you might try translating this into a certain number of degrees, all right, and then see where that would fit into a circle diagram superimposed on a coordinate plane, right? Try to see where you would have a right triangle inscribed into a circle, all right, of 360 degrees. Now, it's also good to recognize certain angles, like for instance, pi over 6, right? At this point, you start to remember is really 30 degrees, all right? If you're a little bit sketchy about how that is so, all right, remember you could convert, right? Unless you have a reference or unless you have something memorized, all right, you could convert an angle like pi over 6 to a certain number of degrees via the appropriate conversion factor. In this case, it's going to be 180 over pi. Pi's cancel. The difference, pardon me, the quotient, or the product in this case, would be 30 degrees. Right? The other one is very similar. Well, let me just complete this thought. If you have 30 degrees, you're probably going to use relationships from this particular special right triangle. The other one, 5 pi over 4. If you were going to convert to degrees to see where it would, reside in your circle, you would appropriately choose 180 over pi again for the cancellation effect, right? You could multiply top times top, get whatever you want, bottom times bottom 1, and get whatever you want, or try to simplify first, right? 4 and 180 are both divisible by 4, right? 4 divided by itself is 1. 180 divided by 4 is actually 45, right? The leftover 5 times the leftover 45 is 225. So this really is 225 degrees, right? Neither of the special right triangle relationships uses the number 225. However, it probably, the types of problems that you're going to get would give you a situation that these could be references, right? So here's a circle, and if you had, recognize this as 0, 90, 180, 270, and 360 is a complete circle, reading this way, of course, counterclockwise. 225 would have to be somewhere in the third quadrant. Quadrant 3, not quadrant 2, or quadrant 1, or quadrant 4. All right. One thing that is good to do is draw the picture like so. Then again, draw your right triangle like this. Right. Acknowledge, yes, that's what 225 would be. But using 180 as a point of reference, how much would the angle actually be just between this part of the x-axis and where the line is actually stretching towards the edge of a circle? All right, it's the difference of basically 225 and 180, right? Which is 45, which means you're going to use angle relationships pertaining to this special right triangle for that particular radians, pi radians, right? So in alphas and such. The one thing that you really need to do is draw this picture, because the one thing that's going to be left out without it is what the signs will be, right? If you have a coordinate comprised of x values and y values at this point, all right, they're both going to be negative because they're in the third quadrant. You need the picture to help you identify that, all right? Anyhow, if this is really $225 minus 30, you're going to fit them basically in each of these respective places. Right. And then figure out what the ratios are as appropriate. All right. Or you could just write them, in the radian form. All right. It's not going to hurt to do that. All right. I prefer degrees personally, but if you may have to, have to change your degree mode. Change your mode if you're using a calculator, depending upon which you start with. All right. Anyhow, will be the cosine of 5 pi over 4, cosine of pi over 6, the sine of 5 pi over 4, and the sine of pi over 6 that you would substitute. Okay. Now, can you get your calculator to figure this out for you? Possibly. All right. And I'll double check. All right. But let's do it by hand first, and then have our calculator verify the results. All right. What I'd really like to do is I'm going to erase some of this just because I need the space. And I'm going to take this half of the identity and sort of stretch it out a little bit so that I can do the work, the intricate work underneath it immediately. trying not to erase this stuff. All right. So we have this established. 5 pi over 4 minus pi over 6. And now we are going to basically substitute each of these trig functions with the respective ratios that those angles would produce. Right? The cosine of an angle, right, that really pertains to the 45-45 situation. Right, that's what 5 pi over 4, otherwise known as 225, really is. This is our reference triangle, right, of the two. Would produce this relationship, right? A cosine is essentially an x value over an r value, right? Having drawn this much of where 225 is located in respect of a circle, right? We will identify what the signs would be appropriately of x's and y's. Okay. Well, if this is where 225 really lands, and cosine is really involving an x in respect of this angle, it's the adjacent, all right, then it's going to be a negative, all right. Adjacent to 45 is 1. Maybe I'll just superimpose that. So this is really negative 1, all right? And then the radius would be square root of 2, all right? Could you rationalize the denominator at this point? I suppose you could, but maybe resist the temptation to do that just yet, right? Anyhow, that's just this first cosine, all right? Now we'll do the next one. The cosine of pi over 6, all right? Pi over 6 is really 30 degrees, so we're going to use our special right triangle, namely this one. All right, cosine again is what is adjacent to the angle of 30. All right, it's an x value again, right, over an r value, adjacent over hypotenuse, if you would prefer to call it that. All right, using these relationships, the square root of 3 over 2. All right. We might rationalize this for the sake of combining it later more cleanly, but let's finish these other two first. Might get a little messy, so I'll probably have to erase something. All right. If we now fill in for this one, sine of an angle, whatever the angle is opposite over hypotenuse, so it's a y, right, over an r. Don't forget there's a plus in between here. This angle of 225, 5 pi over 6, whichever you prefer, all right, remember, lands you in the third quadrant, so your y value would have to, you remind yourself it's a negative, really, okay? And again, 225 pertains to the 45-45 situation, all right? Why? Because this angle, how come? Because this angle that would be in here in relation to 180, stretching down to 225, produces a 45-degree angle. All right. Anyhow, y in the 45-90 situation is once again 1, and the hypotenuse is the square root of 2 specifically. All right. Save that, and we'll do this one more time. The sine of pi over 6 produces a 30-degree angle. I'm going to erase this just for the sake of space. And sine again is a y value over an r value. Because it is really a 30-degree angle in terms of its sines of x values and y values, they would be both positive. They would be in the first quadrant technically. You would have square root of 3 over 2 in that case. what you would do potentially, especially if you're doing this by hand, is rationalize this denominator. That is the one with the square roots of 2 in it. All right? How so? You would multiply, in theory, by a convenient ratio of 1. Right? I'll sort of draw a little thought balloon here to translate this. If you took this value of -1 over the square root of 2, and you multiplied by 1, it would not change the value of this. It would just change the convenient ratio of 1 that I just elect. All right, will not change the value of this. It's just going to basically change its appearance. Right. So if you're trying to get rid of the square root in the denominator, basically you're going to multiply by the square root of 2 here, and then for the sake of consistency, to make it legal, square root of 2 here. All right. The ratio of something on top of itself, barring the situation of 0, 0, all right, produces the amount of 1. So multiplying by 1, again, doesn't do anything but change the appearance of something potentially. So what you would end up with is this. Top times top, bottom times bottom. You'd have negative square root of 2, negative on the outside, and square root of 2 times itself would just basically produce 2. Right? If you did it according to the product rule, that is combine the radicands 2 and 2, you'd get square root of 4. And the square root of 4 is just 2. So no matter which way you slice it, it'll reduce to 2 as a denominator, which is the whole point. Right? Right. A similar situation would occur here. Right? If you were trying to rationalize this, and that's what that is referred to, rationalizing the denominator, it's just multiplying by 1. It's just 1 disguised to produce a cancellation effect. All right. Basically, get rid of your square root. This is exactly the same thing. Just coincidentally, both -1, -1 here, because the x's and the y's are both negative, and they come from a 45-45 triangle, so the dimensions are 1 and 1. Anyhow, what you would expect if you did this once again, that is, you multiply what you have times 1, a convenient ratio, a convenient disguised form of 1, would give you the same thing. Negative square root of 2 sitting on top of 2. Right? That means that you have this, ultimately. That in front, this is all sitting on one side of equals, the square root of 2 over 2, time what was there, square root of 3 over 2, plus, because that identity has that in between, it's a sum on this side of equals. This next, negative square root of 2 over 2 times the square root of 3 over 2. Okay. What did you get? Let's see. The product rule of radicals says that as long as you have the same type of radical, these are both square roots, all right? You can mesh together the guts here. The radicands can be combined or ripped apart if it's a convenience for you. They're already apart, so I'm going to recombine them. That means that the result here will be negative on the outside, the square root of 6, over 2 times 2, which is 4. Okay? Similar situation here. All right? So you have this. Negative the square root of 6 over 4. And there's a plus in between. Okay. Oh, there's one mistake, I'm sorry. When I did this over here, I was suspicious. I should have gotten a different thing from square root of 3 because I was not using an x here. What was I using instead of an x? Y, right? So that would be, I'm sorry, 1, all right? Opposite, if this is sine of the angle, opposite is 1, all right? Adjacent x is square root of 3. I shouldn't have written that twice. All right, so it's 1/2 here, all right? So that's easier. Dopey. See, this is why I encourage people to write things, because you can see that I make dodo mistakes like that, but eventually I catch them. All right, anyhow, 1 times the square root of 2 is just the square root of 2. Like so, okay? So you have this as an end result here. You have negative the square root of 6 over 4 plus negative the square root of 2 over 4. They're fractions for all intents and purposes. They have a top and they have a bottom each. And it's just adding really, all right? It's a negative added to a second negative, which means that in theory you're getting a bigger negative according to the rules for integers, all right? Anyhow, you legally can add these because they have the same denominator at this point, which means that a slightly more concise form of writing this would be to just simply write it over one denominator rather than over two denominators, right? And then you have this. Negative the square root of 6 minus square root of 2. Right? That means that this is your answer. And the whole point of the exercise was to get the exact answer. What does that mean? It means that if you used your calculator would give you a highly precise answer, but it would never be exact, all right? Because it would always be chopping off infinity at some point because it writes things in the style of a decimal. Whereas if you leave things in square root form, radical form, all right, it's preserving all of the decimal even though you can't see it. It is admittedly less satisfying for that reason, but it's a more correct, it's a better answer because it is all of infinity without looking at it. So you could perhaps do this with your calculator, at least up to a certain point, right? But if you're not so fortunate, you're going to get a decimal that's just chopping off some part of it. Pi over 6. Okay, this is the outcome here. Negative the square root of 6 minus the square root of 2, all right, over 4, all right? You might wonder, well, why don't you try to combine the radicals, square root of 6 and square root of 2? I can't, because remember, in order to combine radicals, not only would they have to be the same index, yes, they're both 2, because they're both square roots, but they would have to have the same radicands, the guts would have to match. And no matter what I do to 6, I'm not going to be able to produce something that's meaningful. It would only factor into the square root of 2 times the square root of 3, right? So they're not going to cancel or anything like that. You're basically stuck with what you have here. All right? Anyhow, this is the exact answer. Let's do another one of these a little bit more neatly. Picking up that marker. Okay. Right. I have to spritz this. Yeah. Forgive me. I don't like to use the spray while I'm working because I'm a little afraid how it's going to treat my eraser here. Not necessarily for the best. I have to get a paper towel. And wash this later. Better. Let me pick out a nice one here. Let's say you're given this situation where you have to, again, find an exact value. Right, but you're not given an obvious sum or difference. You're just given something that is an unusual angle, perhaps. Like, the reason I say unusual is that pi over 12 is not one of the more famous angles, for lack of a better phrase. Like pi over 4 is really 45 degrees. Pi over 3 is really 60. Pi over 6 is really 30. All right, this is something else. All right, what you can try to do, all right, is try to break it into whatever is given. Try to break the given angle into, keep picking up that marker, I put that over there, so stop doing that, into either a sum or a difference. Right, because then if you do, you could take advantage of one of the sum or difference identities, right? Now it's not always obvious what you're going to go with, but here's some rationale. All right. These are the superstars, all right? Pi over 4, pi over 6, all right? Pi over 3. All right. Pi over 4 is really 45 degrees. All right. Pi over 6 is really 30 degrees. Pi over 3 is really 60 degrees. All right. And these two pertain to this triangle. Pi over 4 pertains to this triangle. 1, 1 square root of 2. All right. So if you see a number down here, 12, that you can factor into one of the, and actually we work in all cases, you can in theory break this into, something else. All right. In tandem, let's see. It's probably the pi over 3 and the pi over 4. And the reason I say that is because let's say that you broke this up into a difference specifically. The cosine of two things subtracted. Forget that there's a pi here for a second. If you just read it as 1/12, all right? Start with denominators that look like this, 12 over 12, all right? What two numbers, when subtracted, would produce 1? Maybe trying to, in the long run, incorporate one of these three, right, or two of these three, right? Well, 4 minus 3, when subtracted, would produce 1, right? And since it's really just pi over 12, it really is 1/12 of pi, right? So 4 pi over 12 and 3 pi over 12 are two viable options. Right? There might be something else, but this is the one that is occurring to me. Okay. If you reduced these fractions and had a common denominator in order to subtract them to produce this result, if you reduce these fractions, 4/12 would reduce to 1/3. All right, 4 divided by 4 is 1, 12 divided by 4 is 3. A more concise way of writing that would be pi over 3 strictly. If you reduce this fraction, 3/12, that is dividing each by the GCF of 3, all right, you would get 1/4 of pi, since it really is some fraction of pi. And a more concise way of writing that would be pi over 4. Right? And now at this point, we have something that we can involve the superstars here, all right, in one of our identities, all right? The cosine difference formula, difference identity we had just used, as a matter of fact. So let's see. Let me erase this space. And I'll refer back to this. Let me say again, there's an older handout that I would keep around as well, namely this one, right? This one that has your reference angles. Here's 30 degrees, 45, and 60 again, what they correlate to in pi radians. And then if you trace the same color, all right, you'll see which relates to which, all right? Pi over 3 is 4 pi over 3, perhaps with different signs, because it's in the third quadrant, but nonetheless. All right, they'll both be a 60-degree angle in relation to, 0 or 180, all right? Similarly, 45 is 225, as mentioned before. Okay, so keep that around so that you could use it as a reference. It will help you position something if you feel a little, iffy about it. Position the triangle in the appropriate quadrant. Okay. All right, so now back to this, all right? Just coincidentally, all right, we're gonna go with the difference formula for cosine, all right? Because that's the way this worked out, pi over 6. Again, there might have been some other way to break this up, but this is the way that it occurred to me offhand, all right? So we're gonna go with this. Right, the cosine of alpha minus beta is equal to the cosine of alpha, the cosine of beta, plus the sine of alpha and the sine of beta. All right, we're just going to be incorporating these green incarnations of the 4 pi over 12 and 3 pi over 12. Okay. Good. All right. That looks a little too much like a delta, but it's supposed to be an alpha, I swear. Anyhow, pi over 3 is our alpha. So it would be here and here respectively. And pi over 4 is our beta, our second angle. So it would be here and here respectively. Okay. Since the angles happen to be the typical 3, they really are all in the first quadrant. All right, so you don't have to worry about signs really. Be careful. Right, because as you saw in the last problem, we are going to use the 30, 60, 90 or the 45, 45, 90 reference special right triangles, but, all right, do draw a picture like so, all right, to make sure that you're in the appropriate place, right? If you know that this is really 30 degrees, then yeah, all right. You're only going to be dealing with positives in the first quadrant. Positive x's and y's, right? If you're in the second quadrant, then you're going to have a negative x and a positive y, right? If you're in the third quadrant, then they're both negative, negative x, negative y. And if you're in the fourth quadrant, positive x and negative y. So you do need to take that into consideration based upon the actual angle that you calculate. 225, as before, was in the third quadrant. Yes, we're using 45 as a reference, right, to get the ratios correct, right? But that basically decides whether you have negatives or positives, okay? So be careful, all right? Anyhow, and this space again. Having my triangle on hand, 30 square root of 3, 1, 2, and I'm going to need this one as well, the 45, 45, 1, 1 square root of 2. We could figure out systematically what these ratios will be. All right, first one. Cosine is of an angle, right? And it is, in this case, a 60, all right? Is adjacent, all right? Adjacent over hypotenuse, right? So what would be if this is oriented like so, all right, as a 30 along the x-axis, all right? And this would be a 60, in fact, here, right? This would actually be 1, right? The x value would actually be 1 in this case, rather than square root of 3, which it normally is, just for the fact that this is a 60 rather than starting out as a 30, all right? What is adjacent to 60 in this orientation? 1, right? What is adjacent to 60 in this orientation? It would have to be 1, right? So it's 1, right, for cosine on top here, and the hypotenuse is still 2. Okay. Bear with me, I'm going to straighten up my pipe pages here. Okay. Next one. The cosine of pi over 4. All right. In that case, because there are two similar angles here, 45 and 45, you can't screw that up. All right. Adjacent over hypotenuse would be 1 no matter which orientation of your triangle. So it'd be 1. In this case, we're going to have to rationalize the denominator later, so we have square root of 2 for right now for the hypotenuse. The sine of 60 degrees, all right? Sine is opposite of the hypotenuse. So if you're looking at the traditional triangle as 30 in this orientation, and 60 would be up here, opposite of 60 would be square root of 3 in this case. The opposite of this of 60, oriented like so, would be square root of 3. So it's square root of 3 over the same hypotenuse of 2. And then the next one, sine, again, opposite of 45, it's not going to matter, no matter what the orientation. It's going to be 1 over the square root of 2. All right. We will try to combine whatever we can. Right? The things that have radicals in the denominator, I'm going to rationalize the denominator. How so? Again, by multiplying by the denominator to both the top and the bottom. Right? So that will cause a cancellation effect in terms of the radical sign. All right. What you'll end up with is this. If you multiply this by its denominator, above and below, is that you get the square root of 2 above the line on purpose, all right? And the square root of 2 times the square root of 2 is that thing squared, which is there'd be a cancellation effect. Or you could say the square root of 4, same effect. All right, you'd end up with 2 as a denominator, all right? That means that you'd have 1/2 times the square root of 2 over 2. And on this side here of plus, you'd have, for this one, the same thing. You'd have to rationalize. You'd end up with, since it has the exact same numbers, the square root of 2 over 2 would be the end result. A radical of the same index, they're both square roots, can be combined into one radical by a multiplication. Square root of 3 times square root of 2 is the square root of 6. I'll just write it like this for right now. But it's going to be 6 eventually. Let me put this here as I'm running out of space again. Okay, the way this first fraction would work out is top times top. The square root of 2, bottom times bottom, 4. Okay, the way these would work out is, as I mentioned, the square root of 6 from multiplying the bottom times the bottom is again 4. Since they happen to have the same denominator, legally speaking, you can add these. So a slightly more concise incarnation of this, all right, would be the same denominator just written once, right? And then these things on top. You're stuck with these though because there is no convenient way to recombine these into one term. If you factored the square root of 6, you'd get the square root of 2 times the square root of 3, which is what it came from, all right? And there'd be nothing on the outside. In other words, what I'm getting at is that you wouldn't have something like this, like 1 square root of 2 plus, 1 square root of 2, in which case you would have 2 square root of 2, right? That's not going to happen in this case, right? So you're basically stuck with this, right? This is the exact answer. And again, it's not a warm fuzzy answer because we're kind of used to having decimals and automatically gravitating to our calculator. But this is a better answer because it preserves all of the infinity of these irrational numbers without having to write them out, right? So it is truly exact. Now to prove a point, to a certain degree of precision, let me at this moment, type into the calculator what would we get, because I'm curious, right? I will type this straight into our calculator, see what the decimal is, and I will type this into our calculator and see if it matches, all right? At least to the degree of precision that a calculator is capable of, which is like 10 digits, Okay. Let's see. I may have to change modes. Let's see. Pi, remember, is 180. So if you took pi and divided it into 12s, what actual number of degrees would that be? Right? That would be 15 degrees. Right? This is essentially asking what is the cosine of 15 degrees without really consciously thinking about it. Anyhow, since my calculator happens to be in degree mode already, I'm going to hit cosine of 15 and then I'll record what the decimal is. Apparently it is 0.965, whatever it is. 0.965, whatever it is. All right, I'm not rounding it. All right. This answer, which took advantage of the special right triangle relationships of pi over 4 and pi over 3 and pi over 6, all right, gives us this exact answer. It is no longer a trig function. Think about it that way in terms of progress. All right, you started with something that was a trig function, and you were able to express it in terms of something that is really just purely arithmetic. That's an accomplishment, even if it doesn't seem like a grand one. It really is, though. You've taken something complicated as a non-algebraic transcendental function, code trig functions are transcendental, and made it arithmetic. Now let's see if the square root of 2 plus the square root of 6 over 4, to whatever degree of precision a calculator can give us, will produce the same answer. I'm being very careful, so delete. No syntax errors. Here's how I'm grouping the top, if you're curious. I put these in parentheses as the square root of 2 plus the square root of 6 over 4. So I'm just going to use / to get it done quickly. Enter, and there you have it, folks. Same decimal, 0.965. All right, whatever it is. All right, it's irrational, all right, because it comes from irrational numbers. So there's really an infinity there, all right, of a decimal point, right? But this more concisely and via arithmetic expresses this quantity. Okay. All right, clear out. Let me see. Something else real quick. I want to get my book for a moment and I'll be right back. Just pause me for just 1 second. I think I'm going to leave it at that. Okay. Let me stop here. All right. The whole point of this is to acquaint you with the usage of these identities. All right. So, like I said, make sure that you definitely print this handout because you want to have access to these formulas, right? Specifically section 9 too, right? And next week, we're going to do section 9.3, all right? The double angle, half angle, and reduction formulas. I'll walk you through that, and then on Thursday, the product of sum and sum of the product identities. And then we're done basically with right triangle trigonometry. All right. The week after that is technically finals week. I think what it's looking like is that I'm going to do the same thing that I had done for test number 2, which is I'm going to give you, all right, the thing that I would have given you, which is test number 3, and then potentially the final as well, and you'll have it to look at, all right? But I can't collect it, so I'm kind of in the same situation. Anyhow, for homework, try to do, I'll specify problems for section 9 too, this stuff, all right, just for practice. Okay, thank you guys. I'll see you on Tuesday.